Welcome to this lecture. A wealth of techniques are available for analysis of linear time invariant systems and design of controllers for SISO systems. What a SISO system is? A system that has got single input and single output. In this lecture, we shall try to design a powerful technique for such SISO process. In spite of the wealth of techniques available, still search is on to find suitable and most acceptable technique for PID controller design. We shall see how a simple but powerful control design technique can be developed. Coming to the PI controller for SISO process. Here we have got a SISO process given by the transfer function 4 upon 2 s square plus s, and we have got a PI controller given by the proportional gain 2 and the integral gain 1. The PI controller can also be written in the form of GCS equal to 2 plus 1 by s, which in the standard form becomes 2 times 1 plus 1 upon 2 s. So, the integral time constant becomes 2 seconds. Now, why this process is known as a SISO or single input single output process? The process gives us one output and the process is subjected to one input. Where we get such type of processes? Let us consider this room. The room can be treated as one such process if we try to control the room temperature. In that case, the input to the room could be the cool air that can be injected and the output from the room will be the room temperature. So, we can develop a controller for control of room temperature, and in this case we have got the process GS, which dynamics is given by 4 upon 2 s square plus s, as we have said earlier. But when this controller is employed, we get an oscillatory output from the process. Why do we get such oscillatory output? To understand the logic behind that, we need to analyze the system's dynamics. Let us consider the system's closed loop transfer function, which can be given in the form of G GC upon 1 plus G GC. For analysis, let me assume the dynamics of this controller GC to be in the standard PI control form Kp times 1 plus 1 upon TIS. Then that will give me the closed loop transfer function H Kp 1 upon 1 plus 1 upon TIS times TIS 4 by 2 s square plus s divided by 1 plus Kp 1 plus 1 upon TIS by TIS times 4 upon 2 s square plus s, which can ultimately be available in the form of 4 Kp times TIS plus 1 in the numerator and 2 TIS cubed plus TIS square plus 4 Kp TIS plus 4 Kp in the denominator. So, the stability of the closed loop transfer function or the closed loop system can be ascertained from the denominator polynomial of the closed loop transfer function. If we form the truth table for the closed loop transfer function, in that case the truth table assumes the form of s cubed S square, S1, S0 with the coefficients of the row having S cubed H 2 Ti, 4 Kp Ti. For this Ti and 4 Kp are the coefficients, and next from this cross multiplication and manipulation we get the coefficient of S1 row H 4 Kp times Ti minus 2 0 and then 4 Kp in the last row. What we get from this root table? When the coefficients of the first column possess the same sign, in that case the system is stable. The closed loop system must be stable. When Ti equal to 2, what happens? At that time both the coefficients of this row will be 0. When Ti equal to 2, I get the coefficients at 0 0. What that implies? That implies that the closed loop transfer function will have two poles located on the imaginary axis. That means the system response will be oscillatory. There must be a pair of complex conjugate poles in the S plane, and which implies that the system output, closed loop system output might be oscillatory. Exactly that is what is happening when Ti equal to 2. As you have seen, since the integral time constant is Ti equal to 2, giving us a gain of 1 here, as we see, because we can express the PI controller in the form of 2 times 1 plus 1 upon 2s, as we have seen. So, when Ti equal to 2, we get an oscillatory output from the system, but when Ti will be greater than 2 or Ti is very large compared to 2, in that case we must obtain a stable response from the closed loop system. But when Ti is less than 2, the closed loop system will yield us an unstable response, or the response, output response will explode. This is how one can design a PI controller for the process given as 4 upon 2 S square plus S. The Ti should be greater than 2 to obtain some stable response, not like this. Next, let us attempt to design a PID controller for the same process. A PID controller can be designed with the same analysis, using the same analysis. Let me start with the closed loop transfer function, assuming the form of the PID controller. Let the PID controller be given as GCS equal to Kp 1 plus 1 upon TIS plus TDS, and we know our process to be 4 upon S square plus 2 S square plus S. Thus, that will give us the closed loop transfer function as GGC upon 1 plus GGC, which can be obtained after simplification in the form of 4 Kp times Ti Td S square plus TIS plus 1 in the numerator and 2 Ti S cubed plus Ti plus 4 Kp Ti Td times S square in the denominator, along with 4 Kp TIS plus 4 Kp. Now, when a PID controller of this form is used in the series compensation scheme, we get the denominator polynomial of this form. Now, again let me form the Ruth table. So, forming the Ruth table as S cubed, S square, S1, S0 with coefficients as 2 Ti, 4 Kp Ti, then here we have got Ti plus 4 Kp Ti Td and here 4 Kp. Now, the next coefficient can be expressed as 4 Kp Ti minus 8 Kp upon 1 plus 4 Kp Td, and this is 0. Then the cross multiplication like this and this divided by this will give us 4 Kp as the coefficient of the last row. So, the closed loop system will give us a stable response, time response, when all the coefficients of the first column have same sign. So, let me assume Ti is greater than 0, then this becomes positive. When Kp is greater than 0, then this becomes positive, and when Kp Ti Td is greater than 0, Td is also greater than 0, we get this coefficient as positive. What about this coefficient? This will be positive provided Ti is greater than 2 upon 1 plus 4 Kp Td. So, this can be expressed in this form. When Ti is greater than 2 upon 1 plus 4 Kp Td, in that case the coefficients of the first column will be positive, thus implying that the closed loop system will have a stable time response. It will not blow out. Now, with the choice of Kp greater than 0, Td greater than 0, obviously one can get some constant on Ti. Ti is greater than some value. If that is met, if this condition is met, certainly we will get a stable response from the closed loop system. For the time being, let us assume Kp equal to 4, let Td equal to 1. When Kp equal to 4 and Td equal to 1, then the condition gives us Ti has to be greater than 2 upon 17. That is same as Ti is greater than 0.118 approximately. So, if we choose a Ti value which is greater than 0.118 with the choice of Kp equal to 4 and Td equal to 1, certainly we will get a stable time response from the closed loop system. Let us assume Ti to be 4, we are far off from this value. So, certainly it will ensure stability of the closed loop system. So, when Ti equal to 4 along with Kp equal to 4 and Td equal to 1, what sort of response we expect from the closed loop system? We expect such a time response from the closed loop system. The controllers Kp is 4. Now, this is same as Kp Td, which is equal to 4. In this case, Td equal to 1, Kp equal to 4 and Td equal to 1. Therefore, Kp Td is 4. In this case, it is actually Kp by Ti equal to 1, since Kp equal to 4 and Ti equal to 4. Thus, we are getting Kp upon Ti as 1, because the form of the controller is Kp 1 plus 1 upon Tis plus Tds, which gives us upon multiplication Kp plus Kp by Tis plus Kp Tds. Therefore, we have written this Kp value Kp by Ti divided by S and Kp Td derivative term giving us S. So, this PID controller is now giving us a satisfactory response with certain overshoot, response time and so on. Let us try to see how much we get for the choice of Kp equal to 4 Ti equal to 4 and Td equal to 1. When the controller is implemented, then the time response we get is having some overshoot of 18%, overshoot of approximately 18% and settling time of approximately 10 seconds. So, this is what we get, and similarly, when the disturbance load disturbance is applied to the system after time t equal to 20 seconds, we get satisfactory disturbance rejection, as we see, because the disturbance is dying down after some time and it is not having very much peaking. So, what we have got from this, with the choice of the shown Kp, Ti, Td gains or values, the PID controller is giving us a satisfactory time response. Now, question may arise, why we choose Kp to be 4, Ti to be 4 or Td to be 1? Can we choose better than those values to give us still better time response of the closed loop? Yes, it is possible. It all depends on how we are designing a controller for a given SISO process. Now, how to choose appropriate Kp, Ti, Td such that one can meet the design specifications? That can be answered by designing the controllers by some appropriate technique. One such technique, powerful technique, will be discussed in this lecture. Let us go to some analysis now before going to the powerful technique. When the process is assumed to have the form Gs equal to K upon S square plus alpha 1 S plus alpha 0, and when the controller GCS is assumed to have the transfer function Kp 1 plus 1 upon TIS, a PI controller for a all pole single input single output process, we get the closed loop transfer function Ts expressed as GGCS upon 1 plus GGCS H K Kp TIS plus 1 divided by TIS times S square plus alpha 1 S plus alpha 0 plus K Kp TIS plus 1. Now, this can be simplified further and expressed in the form of TIS plus 1 by Ti upon K Kp S cubed plus alpha 1 Ti by K Kp S square plus alpha 0 plus K Kp Ti by K Kp S plus 1. Why are you doing like this? So that with the assumption of S equal to beta Sn and beta cubed equal to K Kp by Ti, it is easy to get the closed loop transfer function in the normalized form given as Tsn H G Gc Sn upon 1 plus G Gc Sn in some convenient form, which can be written as Ti beta, this will be Ti beta Sn plus 1 upon Sn cubed plus alpha 1 by beta Sn square plus alpha 0 plus K Kp by beta square Sn plus 1, which can be written in the generalized form C1 Sn plus 1 divided by Sn cubed plus d2 Sn square plus d1 Sn plus 1. So, where are we doing all these analysis? When we have some all pole process transfer function and a PI controller of this form, the closed loop transfer function can always be expressed in this simple, convenient, generalized form. Had there been a fourth order all pole process dynamics, in that case what we will get? The closed loop transfer function in that case Tsn will be simply of some C1 Sn plus 1 in the numerator along with Sn 5 plus D4 Sn 4 plus D3 Sn 3 plus D2 Sn 2 plus D1 Sn plus 1. So, this is why I am calling we are getting some generalized transfer function, because irrespective of any order of the process dynamics, if the process dynamics is available in the all pole form, in that case it is always possible to get the standard transfer function which is expressed in the form of standard closed loop transfer function expressed in the form of having one numerator in the transfer function and having denominator in this convenient form, and where we will have the denominator expressed as some Sn to the power a n plus d n minus 1 Sn to the power n minus 1 plus and so on till 1. So, this closed loop transfer function is assuming some typical form. If it is possible to find a convenient, a satisfactory closed loop transfer function which is of the form C1s plus 1 upon Sn cubed plus d2 Sn square plus d1 Sn plus 1. If it is possible to get set of d2 and d1 values for some chosen C1 by optimizing some performance index, in that case what will happen? We may get a transfer function which will give us desired time response of a closed loop system. That is the objective. Then from back calculation, since d2, d1 are made up of nothing but the coefficients or the parameters of the controller, one can easily estimate the controller parameters. So, what we have been doing? We are trying to find some standard transfer function which are known to us and which are tested also, that their time response will be highly satisfactory. Then the closed loop transfer function can be used by back calculation to calculate the unknown parameters of a controller, which will definitely yield very satisfactory closed loop performance of a closed loop system. So, we will see how to calculate some standard transfer function, how to find some suitable standard transfer functions of different order. Consider a third order transfer function which can be given in the form of T s equal to y upon r s equal to C1 s plus 1 divided by s cubed plus d2 s square plus d1 s plus 1. This is called a standard transfer function, because we have seen that with appropriate d2 and d1 with a choice of C1, this transfer function, closed loop transfer function, gives us quite satisfactory time responses what we wish to have from a closed loop control system. Then the error function can be obtained as r minus y upon r, which is same as E upon r, as equal to s cubed plus d2 s square plus d1 minus c1 s divided by s cubed plus d2 s square plus d1 s plus 1. Then the error function we obtain in that form. Now, this error can be minimized using the performance indices In this case, how using some ISTE performance index, one can minimize and find the optimum values of C1, D2 and D1 is explained. The ISTE criterion is expressed as 1 upon 2 pi j integration from minus j infinity to j infinity f s times f minus s ds, where f s equal to partial differentiation of E s. How to compute the coefficients C1, D2, D1 using some minimization routine? One can easily use Astrom's recursive algorithm. Writing some simple MATLAB code, it is easy to minimize this performance index. Minimization of this performance index yields a set of C1, D's and C1. So, a set of D's means all the D coefficients D2, D1 and so on, and C1 can be obtained, and that ensures us the minimum value of the IST criterion. One can use the ISE criterion also, but often it is found that the IST criterion, minimization of IST criterion often leads to very satisfactory closed loop performances of a closed loop system. How such values are obtained, we can see. So, using the ISTE optimization or minimization, one can obtain D2 and D1 coefficients for various C1. This gives the x axis goes from 0 to 8 and the y axis goes from 1 to 10. So, this is the beginning point for the y axis. So, this is what we have got D2 and D1. So, for any C1, suppose C1 equal to 4, I can find the optimum values for D2 and D1 from here, optimum values for D2 and D1. When C1 equal to 0, the optimum values of D2 is this much and the optimum values for D1 is this much. So, this set of optimum C1, D2, D1 gives us a standard third order transfer function, and when the closed loop transfer function with the use of a controller becomes a standard third order transfer function, then in that case we get definitely a quite satisfactory time response from the system. What sort of time responses are expected from the standard transfer functions? Let us see. When C1 equal to 0, the closed loop time response will be of this form. When C1 equal to 0.5, we get you see, when C1 equal to 0, we have got finite D2 and D1 values. Similarly, for each C1 values, we have got the set of these values, or D2 is something and D1 equal to something. All those values can be obtained from this plot. So, for any given C1, always we get some D2 and D1. These optimum values of D2 and D1 for any given C1 always yields a quite satisfactory time response of the closed loop system. Why do I call this quite satisfactory time response? If we look at the responses, we see that the responses are having at most 5% of overshoot. Similarly, the responses have got settling time from 5 to 7 seconds, and the responses has got 0 steady state error. These are quite desirable while designing a closed loop control system or while designing a controller. So, the standard transfer functions are giving us quite satisfactory time responses of the closed loop system. Then from the back calculation, we can find out the parameters of a controller using the expressions D2, D1, C1 and expressions for beta. We shall see in the form of some example, in the simulation example, how convenient controller can be designed. Before going to that, we have seen that the standard transfer function can be expressed in this form, where T s is the closed loop transfer function having the numerator C 1 s plus 1 upon s cubed plus d 2 s square plus d 1 s plus 1. Its loop gain can be obtained. How do we get loop gain? Because we know that T s is nothing but G G C s upon 1 plus G G C s. So, which can be used to get G G C s H T s minus 1 upon T s. With little manipulation, it is easy to see that one can obtain G G C s H T s minus 1 upon T s. So, when T s is given in this form, then G G C s will be available, can be obtained in the form of C 1 s plus 1 divided by s times s square plus d 2 s plus d 1 minus C 1. Where are you getting this closed loop gain? From the loop gain, it is easy to get the gain margin, phase margin of the closed loop system. So, these gain and phase margins will give us information about frequency response of the system. So, when the set of C 1, D 2 and D 1, which are optimum as far as the third order standard transfer function is concerned, are put in this expression and the gain and phase margins are found, definitely one will get very satisfactory phase and gain margins. Let us go to the simulation study, where we will make use of the standard form based controller design. A third order standard transfer function will be used to design a PI controller for a all pole SISO process. So, let us assume that the process dynamics is having all poles, means having poles only with a static gain of k and its denominator polynomial expressed as s square plus alpha 1 s plus alpha 0. Then we will go back to some specific form of transfer function and design the PI controller. Let the PI controller be expressed in the transfer function h Kp plus Ki upon s, which can again be expressed in the standard form as Kp 1 plus Ki by Kp s. So, for each in analysis, we have expressed the transfer function of the controller in the form of Kp plus Kis. So, with this process dynamics and PI controller dynamics, the closed loop transfer function becomes Ts equal to Kp upon Ki s plus 1 divided by s cubed by k Ki plus alpha 1 s square by k Ki plus alpha 0 plus k Kp times s by k Ki plus 1. So, the closed loop transfer function can be obtained in this form. Now, assuming k Ki h beta cubed and setting s h beta s n, the above transfer function can be expressed as T s n equal to C 1 s n plus 1 divided by s n cubed plus d 2 s n square plus d 1 s n plus 1, where d 2 equal to alpha 1 by beta. If you see d 2 equal to this alpha 1 by beta, then d 1 equal to alpha 0 plus k Kp by beta square and C 1 equal to Kp beta upon Ki. So, all these comparing this transfer function with this one, definitely one can write the expressions for d 2, d 1 and C 1 in this fashion. Why we are writing in this fashion? Now, you see the beauty of this method. Now, the d 2 parameter is having the plant parameter or process parameter alpha 1 and beta, d 1 is containing the unknown controller parameter Kp and C 1 is containing the unknown controller parameter Kp and Ki both. So, using the optimum values of D2, D1 and C1, it is possible to use back calculation and get the design values for Kp and Ti. This is how one designs a controller using standard form. Now, let us go to the particular case. For our case, as you have seen, when the process dynamics is given as 0.5 upon S square plus 1.595 S plus 1.62, at that time K becomes 0.5, alpha 1 becomes 1.595 and alpha 0 becomes 1.62. That is what we have got. Then substituting these values and using the plot for the optimized coefficients, when C1 equal to 0.5, D2 can be obtained as 1.595 and D1 equal to 2.12, where from we get when C1 equal to 0.5, what are the optimum values for D1 and D2? When C1 equal to 0.5, I can find the D2 to be of this one, which is 1.595. When C1 equal to 0.5, D2 equal to 1.595 and D1 equal to 2.12. So, this is what we get from the plot. Next, but D2 can also be expressed as alpha 1 by beta. Alpha 1 is known to us, thus giving us beta as 1. Alpha 1 is 1.595, whereas D2 is 1.595, therefore, beta equal to 1. Next expression we have got that we have got one more expression K Ki equal to beta cubed, that we have assumed K Ki equal to beta cubed, and since beta equal to 1, therefore, Ki can be obtained as beta cubed by K is given, that is one of the process parameter 1 upon 0.5. So, K becomes 2. Similarly, using the expression C1 equal to Kp beta upon Ki, Kp unknown, since we know now C1, beta and Ki are known, the only unknown Kp can be estimated as 1. Thus, we have been able to design a Pi controller, which is given as GCS equal to Kp plus Ki upon S as 1 plus 2 by S. What is expected from this controller? This controller must give us a time response, which is as we have seen for the standard transfer function. Now, going to the simulation diagram. In the simulation diagram, what we have? We will apply unit step input. So, RT, the reference equal to some unit step input 1, then let the load be also given by some magnitude L equal to 0.1 with the time at which it occurs at time t equal to 20 second. Now, the Pi controller we have designed for the given process is S plus 2 upon S, which is nothing but S plus 2 upon S can be expressed as 1 time 1 plus 1 upon 0.5 S. No, in this case it will be different. Okay. Let us go back to the exact form we have got. I have got 1 plus 2 S. So, in this case, since I am making use of this one, so I will have 0.5 over here, then in that case it is giving us 0.5 S plus 1 and we are not getting. So, that way how can we express this in the standard form? the form I have written is not correct actually. So, to get it in the standard PI transfer function form, S plus 2 by S can be written as 1 plus 2 by S, 2 by S, which is nothing but 1 plus 1 upon 0.5 S. Okay. So, it is in the form of GCS as Kp 1 plus 1 upon 0.5 S, where we have got 0.5 in the form of again Kp 1 plus 1 upon TIS. So, I can say that I have designed a PI controller where the proportional gain is 1 and the integral time constant equal to 0.5, giving us a PI controller in the form of S plus 2 by S. Okay. So, this is how we have realized the PI controller GCS for the process having parameters k equal to 0.5 and alpha 1 equal to 1.595 and alpha 0 equal to 1.62. So, what sort of output we will expect from this one when this is simulated? Definitely we will expect a quite satisfactory time response from the closed loop system. As we expect, the output here is having almost settling time of 5% and overshoot of 5%, settling time is of 8 seconds as expected. So, what we get basically? We get a closed loop transfer function response very much similar to that we get from a standard closed loop transfer function. Coming to the other analysis, frequency analysis or frequency response of the closed loop system, the Nyquist diagram of the closed loop system can be drawn in this case, for which we need to get the loop gain GC G S. The loop gain for this will be S plus 2 upon S times we have got 0.5 by S square plus 1.595 S plus 1.62, sorry, we have got 1.62. So, using this loop gain or loop transfer function, one can obtain the polar plot or Nyquist diagram. What information we get from Nyquist diagram? The phase crossover point is somewhere around here and the gain crossover point will be somewhere around here. As we see, measure this span and inverse of this will give us the gain margin. This span is very small because this span, total span from here to here equal to 1. So, we will have a very good gain margin for the system. Similarly, if I draw a line from here to here and measure this angle, I will get a very good phase margin for the system. What are those values? Let us see. Using the analysis, one can obtain those values at some gain margin of 12 in absolute value term and the phase margin of some 65 degree. We know that a gain margin of greater than 2 and a phase margin of greater than 30 degree ensures a robust control system or a quite stable closed loop system. So, as far as stability of the closed loop transfer function is concerned, we are far off from those values and therefore, we have got a quite robust closed loop control system. Now, same information can be derived using the Bode diagram. So, using the Bode diagram, we can track the phase and gain crossover frequencies and then the phase and gain margin. So, phase crossover frequency, if I draw a line over here at 180 degree, I will get somewhere like this, and that will give me from the phase crossover frequency we can draw a line vertically and find how much you are away from the 0 dB. This much will give you the gain margin. So, minus of this value will give us the gain margin. So, we get a quite high gain margin for the system. Similarly, let us track the gain crossover frequency. So, this is the gain crossover frequency, the frequency at which the gain of the system is 1, or in dB the gain of the system is 0 dB. So, we will get the gain crossover frequency of this magnitude, for which let us find what is the phase angle at that time, how far you are from the minus 180 degree, we are far off, which gives us a phase margin of approximately some 60 to 65 degree. Thus, what we see that the closed loop system is not only giving us a quite satisfactory time response, also we are getting a quite satisfactory frequency response from the system. Now, there is one problem associated with this method, that one has to make use of series form of PID controller in place of the parallel form of PID controller. What a parallel form of PID controller is? We write a controller given by the transfer function GCS as Kp times 1 plus 1 upon TIS plus TDS as the transfer function for a parallel form of PID controller. When a parallel form of PID controller, then the controller itself is introducing two zeros. If you simplify this one, it is giving us an expression in the form of Kp Ti TDS square plus TIS plus 1 upon TIS. So, from this expression we say that the transfer function of the PID controller, which is in parallel PID control form, gives us two zeros, introduces two zeros in the closed loop system and one pole at the origin. So, when we will have two zeros given by the controller and the plant is all pole system, in that case what happens, the closed loop transfer function will be having two zeros in the numerator. That means, the standard transfer functions will have two zeros, for which it is very difficult to find the coefficients d1, d2 and so on. The point is that we have got standard transfer functions expressed in the form of C1s plus 1 upon, then here we can have any order s to the power n plus d n minus 1 s to the power n minus 1 plus and so on, but in the numerator we have got 1 0 only. So, how to handle those situations? To handle those situations, what we have to have? We can always have a parallel form, a series form of the PID controller, in which case one of the 0 of the PID controller is to be cancelled with one of the pole of the all pole transfer function. How to select, how to make cancellations? We should choose the TD of the controller as 1 upon d1, and this d1 should be as small as possible. D1 should assume some small value. In that case, we are assuming that a pole is cancelled, a pole which is located far up from the left half from the origin of the S plane is cancelled, is getting cancelled with the derivative term of the series PID controller. Then we can make use of a series form of PID controller and a all pole process model to design controllers using standard form. Now, what have we learned from the lesson? We have seen how a standard transfer function results in satisfactory time and frequency responses, and how a standard transfer function can be used to design the parameters of a P, PI or PID controller using back calculation. But there is one limitation with the method, the process dynamics has to be available in the form of all pole transfer function form, and the form of controller one can use when we have a PID controller is that a series PID controller. Now, we will go to the points to ponder. What are some limitations of the method? What happens when a process dynamics is available in the first order plus date time transfer function form? When the process dynamics is available in this form, one can always get the process dynamics expressed in the form of k of n 1 minus 1 plus theta s T 1 s plus 1, of course, when theta is a small number, small value. When that is not so, make use of plant order reduction technique or process order reduction technique to get the plant dynamics available in the form of all pole transfer function. Second point to ponder is that why do we design series PID controller? As we have discussed that a series PID controller enables us to cancel one of the 0 of the controller with one pole of the all pole transfer function of the process, then thus giving us 1 0 in the standard transfer function. If that is not the case, in that case when we use one parallel PID controller, 2 zeros appears in the standard transfer function, and it is very difficult to find the optimum values of D's and C2, C1 in the case of parallel PID controller. That is why we need to design series PID controller. That is all in the lecture.